Picture this. The invisible threads of cosmic energy stretching across the universe, and right here, enveloping our own extraordinary planet, a dynamic and often unseen electrical ballet.
Hmm.
That's the kind of wonder we chase here at the All Sorts podcast. If you're drawn to the hidden stories our world and the cosmos whisper, then you're absolutely in the right place.
Definitely.
You, our listener, are the explorer we're creating this for. And if you want to fuel your mind with more incredible discoveries, make sure you become part of our community on YouTube. Like, share, and subscribe to the All Sorts podcast. It's how you join the adventure.
Yeah, absolutely. We've got a whole archive of past deep dives waiting to ignite your curiosity.
And the conversation doesn't end with the audio. Connect with us beyond the sound waves on X, Instagram, and Threads. We're always eager to hear what sparks your interest.
We really are.
Okay, let's dive straight into something truly electrifying today. We're going on a deep dive into the world of high-altitude lightning and those fleeting, almost mythical flashes that happen way up above the clouds. Transient luminous events, or TLEs as they're known.
Right. And what's fascinating for you to consider is that we're not talking about the everyday lightning you see during a typical thunderstorm.
Oh.
These are electrical discharges that occur many miles above where regular lightning forms. It's a whole different realm of atmospheric electricity.
Exactly. And we've got two really interesting pieces of information to guide our exploration. First, we'll be looking at a real-world challenge: how to protect remote mountain huts in Colorado from the very real danger of lightning strikes.
A practical application.
Yeah, and then we'll take a giant leap upwards with a master's thesis that examines TLEs using all sorts of observation tools, from cameras on the ground to sophisticated instruments orbiting in space.
So the mission we have for you on this deep dive is to truly understand these high-altitude electrical phenomena. We want to explore their various forms, what they look like, where they occur, and uncover the ingenious methods scientists are using to study these incredibly brief but powerful events.
Okay, let's start by heading up to those high altitudes and talking about lightning in the mountains. Now, when you think of lightning, you probably picture a flash during a storm. But in high-altitude environments, it's a persistent and serious threat.
Yeah, it really is.
You might be surprised to learn that in Colorado alone, lightning still causes around 4 to 8 fatalities each year. It really underscores the fact that out in nature, it's not about being completely safe, but about understanding the levels of risk involved.
That's a really important point for you to keep in mind. And the case study on the Colorado 10th Mountain Hut System perfectly illustrates this vulnerability. These huts, which provide shelter for hikers, are often situated in very exposed locations.
Right.
Think about it. High elevation means they're often the tallest things around. They're exposed to storms that frequently move in from the southwest, and even the local rocks and the shape of the terrain can make them more likely to be struck. Plus, because they're so remote, any damage from a lightning strike can have significant and lasting consequences.
Yeah, the study points out several factors that make these huts particularly susceptible. Their sheer elevation, being right in the path of those southwest storms, the underlying geology, and even if there are nearby trees that have been hit before, it can almost create a pathway for future strikes.
That's right.
And then there's the first-hand experience of the hut staff who have witnessed some pretty close calls.
When you're trying to protect these remote structures, the solutions aren't always obvious. The study looked at a few potential ways to reduce the risk. The first thing that might come to your mind is lightning rods, either a single rod or multiple ones strategically placed.
Sure, the classic solution.
Yeah, the classic. They also considered using masts with overhead wires, similar to how power lines are sometimes protected.
But that overhead wire idea was quickly dismissed, largely due to the cost and, understandably, the visual impact it would have on these pristine wilderness areas.
Exactly, yeah. You go to a remote mountain hut to connect with nature, not to see a network of wires.
Right.
Exactly. And then there was the, perhaps surprisingly, do-nothing approach. The study notes that the actual probability of a direct lightning strike igniting a fire is relatively low.
Okay.
However, they immediately balance that against the potentially catastrophic consequences. They cite an incident from 2009 where a hut was struck, leading to $750,000 in damage and the hut being closed for an entire year.
Wow, $750,000.
Yeah, that's a huge impact for what might seem like a low probability event.
That really puts the risk into perspective for you, doesn't it? A seemingly small chance of something happening, but with incredibly high costs if it does.
Precisely.
So it sounds like there's an ongoing effort to find the best ways to keep these high-altitude shelters safe. It's a balance between effective protection and practical implementation in these challenging environments.
Absolutely. Now, let's shift our perspective dramatically and journey even higher, far above those mountain peaks and storm clouds, to explore the truly enigmatic realm of transient luminous events.
Okay, TLEs. The name itself sounds like something out of a sci-fi movie. For you, our listener, what exactly are these things?
Well, these are electrical discharges that have only been discovered relatively recently, and they occur in the upper atmosphere, way above thunderstorms.
Way above.
Yeah, the key thing for you to remember is transient. They are incredibly brief, lasting from just a few thousandths of a second up to a couple of seconds at most.
Milliseconds. Wow.
Yeah. And what's particularly interesting is that they are triggered by the ordinary lightning that's happening within or below the storm clouds. So events happening down here are causing these spectacular fleeting phenomena way up high.
So these massive bursts of light happening miles above us are actually linked to the lightning we see during a storm. That's a mind-blowing connection for you to consider.
It really is.
How are these even discovered? It sounds like they'd be hard to spot.
Well, initially, there were just anecdotal reports from pilots who occasionally saw strange flashes above severe storms. But the first real scientific breakthrough happened in 1989 when a researcher, Dr. Robert France, almost by chance, left a low-light TV camera running overnight, aimed at the night sky.
No way!
Yeah. It captured the very first video evidence of a TLE occurring high up in the mesosphere.
Oh,
Talk about being in the right place at the right time for a major discovery.
That's incredible luck.
It was. And remarkably, in the same year during a space shuttle mission, more of these TLEs were recorded as part of an experiment called the Mesoscale Lightning Observation Experiment.
Oh!
That really opened up a new area of atmospheric research. Now, scientists classify TLEs based on a whole range of characteristics for you to understand their shape, their size, the colors they exhibit, the altitude at which they appear, their origin in relation to the lightning below, and how long they last. It's a complex but fascinating classification system.
So it's not just one type of high-altitude flash. What are some of the different categories that scientists have identified for you?
There's quite a variety. Some of the main types you might hear about are elves, sprites, and halos. Then there are different kinds of jets that shoot upwards: blue jets, blue starters, and the very powerful gigantic jets.
Jets shooting up.
Yeah. And more recently, researchers have identified even more elusive and oddly named events like trolls, gnomes, pixies, and even ghosts.
Ghosts. That sounds really mysterious for you to think about.
It does, but the names often come from their appearance or how they were initially observed. For instance, elves is actually an acronym: emission of light and very low-frequency perturbations due to electromagnetic pulse sources. So even the names often have a scientific basis.
That makes more sense for you to know. So why is it so important for scientists to study these brief events happening so far above us? What's the bigger picture?
Well, there are several really significant scientific reasons for you to appreciate. Firstly, by studying TLEs, we can gain a much deeper understanding of how lightning itself forms and how electrical energy is transferred throughout the atmosphere.
Okay.
Secondly, these events are believed to play a role in the Earth's global electric circuit, which is a fundamental system that governs our planet's overall electrical balance. And perhaps most surprisingly for you, TLEs might even have a chemical impact on Earth's climate by altering the composition of the upper atmosphere. So these aren't just pretty lights. They could have important implications for our planet.
Wow, that's a lot of potential impact from these fleeting flashes. So how do scientists actually manage to observe something that's so high up and lasts for such a short time? What kind of tools do they use for you to understand this research?
They use a variety of observation platforms, each with its own advantages. Ground-based observatories equipped with highly sensitive low-light cameras are essential.
Right.
But they also use instruments mounted on space-based platforms like satellites, which give a global view. Then there are observations made from aircraft, allowing for targeted studies of specific storm systems, and even high-altitude balloons that can float in the upper atmosphere.
A multi-pronged approach, then.
Exactly. The master's thesis we're discussing really focuses on exploring and describing these different methods used for TLE investigation, giving you a comprehensive overview of how this research is conducted.
Before we go into the specifics of these different types of TLEs and the amazing ways they're observed, maybe we should quickly recap our basic understanding of regular lightning, just to provide a solid foundation for you.
Absolutely. Good idea. So the traditional understanding of lightning for you is that it's an electrostatic discharge within the atmosphere, usually associated with thunderstorms.
Right.
It begins with the separation of electrical charges within the clouds, typically. Positive charges accumulate towards the top and negative charges towards the bottom. Eventually, this electrical imbalance becomes so strong that it overcomes the air's natural ability to insulate.
And that's when you get that initial, almost invisible pathway forming, right? The steps leader that you might have heard about. Think of it like a scout, finding the easiest route down.
Exactly. The stepped leader is a faintly luminous channel that progresses downwards in a series of rapid steps, zigzagging its way towards the ground. Once it gets close enough to the surface, a positively charged discharge rises up from the ground to meet it.
The streamer.
Yes, the streamer. When these two connect, they create a path of low electrical resistance, and that's when the brilliant return stroke happens, traveling rapidly back up to the cloud.
Got it.
That's the intense flash of light you see and the rapid heating of the air that causes the sound of thunder.
And I remember reading that there are different types of lightning based on where that electrical discharge occurs.
Yes, there are 5 main types for you to be aware of. The most common and well-known is cloud-to-ground CD lightning. But you also have ground-to-cloud, GC, where the discharge travels upwards from the ground to the cloud. Intra-cloud, IC lightning, happens entirely within a single cloud. Cloud-to-cloud CC lightning occurs between different clouds, and cloud-to-air, CA, is a discharge that starts in a cloud but doesn't reach the ground, instead dissipating in the air. Cloud-ground lightning is the most frequently studied one.
And even within cloud-to-ground lightning, there are distinctions like positive and negative strikes. What's the difference there for you?
Precisely. Negative CG lightning, which is more common, typically involves a stepped leader with branches extending downwards, and it often includes multiple return strokes, those subsequent flashes you'd sometimes see after the main strike.
Flickering, yeah.
Exactly. Positive CG lightning, on the other hand, often has a leader with fewer downward branches, and those branches tend to be higher up in the cloud. Interestingly for you, positive CG strikes usually only have one return stroke, but it tends to be much more powerful, producing a very bright flash and a loud, low-frequency rumble of thunder.
Ah, the really big boomers.
Yeah, those ones. There are also other less common forms, like bolt from the blue, which can strike surprisingly far away from the main storm cloud, and ribbon lightning, where the multiple return strokes appear spread out horizontally by the wind.
Okay, so that gives us a good foundation in regular lightning for you. Now let's journey back up to the more exotic phenomena, TLEs. Starting with those elves, what makes them unique for you?
Elves are a truly fascinating type of TLE. As we mentioned, their name is an acronym, and they occur at the very highest altitudes of upper atmospheric lightning, around 100 kilometers, that's right at the edge of space for all practical purposes.
100 kilometers, wow.
Yeah. They often appear as diffuse, rapidly expanding rings of light above particularly intense lightning strikes. What's crucial about elves is that they are triggered by the electromagnetic pulse, or EMP, generated by that powerful underlying lightning strike.
Okay, the EMP.
Think of it like a ripple in the electromagnetic field that travels upwards and briefly illuminates this vast, ring-shaped region high above.
So a flash of light way up high caused by an invisible ripple from down below, that's an incredible connection for you to contemplate.
It really is.
What about sprites? They sound a bit more substantial.
Sprites occur lower down in the mesosphere, between about 50 and 90 kilometers altitude. They are much larger than elves, but also quite faint, often appearing reddish in color.
Reddish, okay.
Their shapes can be remarkably varied, sometimes described as looking like giant jellyfish with tendrils reaching downwards towards the clouds, or like a collection of upward-pointing carrots, or even like a ghostly upward firework display.
Jellyfish or carrots? That's quite the imagery.
It is. What's really interesting is that sprites are most often triggered by strong, positive cloud-to-ground lightning strikes, and they can have these faint fibrous streams that extend surprisingly far down, sometimes as low as 30 kilometers.
30 kilometers?
Yeah, that's a huge vertical extent for you to visualize.
Wow, from 90 kilometers all the way down to 30. That's an enormous range. And you mentioned halos. What are those for you?
Halos are these faint, short-lived glows that can sometimes precede sprites or elves. They occur in the lower ionosphere or upper mesosphere, so they're in that transitional zone between the elves and the sprites.
Ah, okay.
They're not always observed, but their presence can give us clues about the conditions in the upper atmosphere just before a larger TLE appears.
And then we have the jets. You said there are a few different types of those that shoot upwards from storms. What should you know about them?
Yes. We have blue jets, blue starters, and gigantic jets. All of these are optical ejections that originate from the tops of thunderstorms and project upwards into the atmosphere.
Upwards, right.
Blue jets were actually the first type of jet captured on video back in 1989. They are brighter than sprites but occur less frequently. They move incredibly fast, at speeds of around 100 to 120 kilometers per second.
Wow, per second.
Per second. So they are very short-lived, but they can be visible to the naked eye under the right conditions.
And what about blue starters? Are they simply smaller or less powerful versions of blue jets for you?
Pretty much. They were discovered a bit later in 1994, and they are upward-moving luminous features that are shorter and fainter than blue jets. They seem to originate lower in the cloud tops and don't reach as high into the stratosphere.
Okay, like precursors sometimes.
Possibly, or just smaller scale events. And those gigantic jets sound, well, gigantic. What makes them stand out for you? They are. These are the most powerful and spectacular type of jet, reaching very, very high altitudes, up to 90 kilometers in some cases.
90 kilometers again.
Yeah, reaching up towards sprite altitudes. They might start off appearing blue, similar to blue jets, but often transition to a reddish hue as they ascend into the mesosphere. Interestingly, data from the 4FSTAT-2 satellite suggests they are quite rare, making up only about 0.3% of all the TLEs they detected.
0.3%. That's really rare.
Very rare. So they're a relatively uncommon but incredibly powerful phenomenon for you to appreciate.
So they're like the rare jewels of the upper atmosphere. You also mentioned trolls. That's another unusual name for you to remember.
Yes, trolls are among the more recently discovered TLEs. The name stands for transient red optical luminous lineaments.
Ah, another acronym.
Yep. They appear as faint red spots near the tops of active thunderclouds and often have reddish, streamer-like features pointing upwards, somewhat resembling blue jets in their direction. What's particularly fascinating is that they often seem to occur after strong sprites.
After sprites.
Yeah, slow-motion video analysis suggests that a troll might actually be a series of upward luminous events originating in the fading tendrils of a sprite. It's like the sprite leaves behind these lingering upward flashes for you to observe.
It's incredible to think that the atmosphere is putting on this complex and colorful light show way above us, and we're only just beginning to understand all the different forms it takes.
Absolutely.
Now, you mentioned that there are different ways these TLEs are observed. Let's delve into some of the key missions and instruments that the thesis highlights for you, starting with what's being done from space.
Okay. Space-based observations provide a unique and invaluable vantage point for studying TLEs on a global scale for you. One key project is ASIM, the Atmosphere-Space Interaction Monitor,
ASIM, right.
which was launched and mounted on the International Space Station back in 2018. It's a major international collaboration, with the Danish Technical University playing a leading role in the science. ASIM is equipped with a suite of instruments, including MXGS, which detects high-energy gamma rays, and MAMIA, which is specifically designed to capture optical TLEs like sprites, elves, jets, and halos. Because it's on the ISS, it has a fantastic view of storms passing below.
So it's like having a dedicated TLE observatory right there on the International Space Station for us.
Exactly. Then there was the Thor experiment, which also took place on the ISS in 2015, led by astronaut Andreas Mogensen.
Thor, okay.
Its mission was to image not only TLEs, but also gravity waves in the atmosphere and the tops of large storm clouds. He used a very sensitive Nikon D4 camera from the cupola module, capturing some truly remarkable footage of pulsating blue jets over the Bay of Bengal.
Pulsating blue jets.
Yeah, it gives you a sense of how visually striking these events could be from above.
That must have been an absolutely incredible sight to witness from up there.
Oh, I imagine so. Absolutely. Yeah. Another significant space-based mission was Formosat-2, a Taiwanese satellite that carried the IJUL instrument imager of sprites and upper atmospheric lightning. IJUL included a sprite imager, an array photometer, and a spectrophotometer. It operated in different modes over its 10-year mission, collecting a vast amount of data and detecting various types of TLEs globally. Elves were the most frequently detected and gigantic jets the rarest.
Right, we heard that rarity figure.
Yeah. Interestingly, they found that elves were more commonly observed over oceans, while sprites tended to occur more frequently over land. There was also a possible correlation they found between the occurrence of elves and warmer sea surface temperatures.
Oh, interesting.
Hinting at a link to more intense thunderstorms below.
That's a fascinating connection for you to think about. Warmer oceans potentially leading to more elves high in the atmosphere. It suggests a complex interplay of atmospheric processes.
It certainly does, indicating a link back to the intensity of the thunderstorms below. Sadly, not all scientific missions are successful. The thesis also mentions Tyrannus.
Ah,
which is a
yes.
French CNES satellite specifically designed to study TLEs and terrestrial gamma flashes. It launched on a Vega rocket, but unfortunately experienced a failure.
Oh no, that's a real setback for the research community.
It is, but it's an inherent risk in space exploration. The thesis also highlights some interesting contributions from Russian experiments, including Tatiana 2, Chibizem, TUS, and RELE.
Okay.
Tatiana 2, for example, surprisingly detected TLEs even in regions without obvious cloud cover, raising some intriguing questions about the triggering mechanisms. Chibizem focused on analyzing the radio frequency signals emitted by lightning. TUS even managed to observe what appeared to be double elves.
Double O's.
Yeah, which is a very rare occurrence. And RELA detected a variety of different electromagnetic waveforms associated with TLEs. It shows that multiple nations are contributing to this field of research.
It sounds like there's a whole fleet of spacecraft, both past and present, dedicated to unraveling these atmospheric mysteries for us. What about observations from closer to home, like from aircraft? What advantages do they offer for you?
Aircraft-based campaigns offer a significant advantage in that they can be strategically flown to target specific storm systems of interest, and they can carry a suite of co-aligned instruments for making simultaneous observations across different wavelengths.
Right, more targeted.
Exactly. The EXL-98 campaign in 1998, for instance, used a Gulfstream II aircraft equipped with multiple cameras and spectrometers operating across a broad spectrum, from ultraviolet to infrared. This allowed researchers to simultaneously observe sprites and, remarkably, the OH airglow layer in the atmosphere, providing valuable context.
Ah, the airglow.
Yeah. Being above much of the atmosphere that can absorb or scatter light gives aircraft a much clearer view of these faint upper atmospheric events than ground-based observers typically have.
That makes perfect sense for you to understand. Less atmosphere in the way means clearer observations. And I also noticed that there were balloon-based missions mentioned in the thesis. What was the focus of those for you?
Yes. High-altitude balloons provide a stable and relatively inexpensive platform in the stratosphere for making extended observations. NASA sponsored a couple of sprites campaigns in the late 1990s and early 2000s.
Sprites campaigns.
These missions primarily focused on detecting the electromagnetic signatures of the lightning that are thought to trigger sprites, using instruments like low-light TV cameras and relying on ground-based support for triangulation to determine the location and altitude of the events. There were also balloon campaigns conducted in Brazil in 2002-2003 that aimed to study the electromagnetic characteristics of the thunderstorms that produce sprites.
Okay.
These missions offer a unique perspective, floating high in the atmosphere but below the altitudes where satellites orbit.
So scientists are really approaching this from every conceivable angle, from instruments on the ground all the way up to sophisticated satellites in space. And speaking of ground-based observations, what are some of the key techniques used down here for you?
Ground-based observations, particularly in regions that experience frequent and intense thunderstorms, play a crucial role in TLE research for you. The thesis highlights some interesting work conducted in Israel and Europe.
Okay.
In Israel, the Elan campaign conducted winter observations of TLEs using highly sensitive, low-light CCD cameras deployed at Tel Aviv University and the WISE Observatory. They successfully captured images of sprites and elves occurring over the Mediterranean Sea.
Over the sea, right.
Yeah. They even employed infrasound arrays, which are essentially networks of very sensitive microphones, to detect the low-frequency acoustic waves generated by sprites.
Sound waves from sprites.
Yes. By analyzing these sound waves, they could estimate the altitude and even the size of these upper atmospheric events. They found these intriguing signals they called inverted chirps.
Inverted chirps, that sounds quite technical for you. What does that tell them?
The inverted chirp refers to the way the different frequencies of the infrasound waves arrive at the detectors. The specific pattern of these frequency changes can provide information about the altitude and distance of the sprite that generated the sound.
Fascinating.
In Europe, researchers have utilized high-speed video cameras, such as the Phantom V7.3 CMOS camera, to analyze the very rapid development and short duration of sprites and halos over the Mediterranean.
High speed, okay.
This high-speed imaging has allowed them to study the different phases of sprite formation in great detail, and have even captured halos occurring just before the appearance of sprites and elves. There have also been very low-frequency VLF observations using specialized magnetic loop antennas, part of systems like
Awesome systems, right.
to study the subtle perturbations in the Earth's electromagnetic field that are associated with TLEs. Data from the Eurosprite 2007 campaign provides insights into the electromagnetic relationship between lightning and these upper atmospheric events.
It's truly amazing how many different and ingenious tools and techniques are being used to study these incredibly fleeting atmospheric phenomena for us. The thesis also briefly touches on the methods used to locate regular lightning strikes. Can you give us a quick overview of those for you?
Absolutely. Ground-based lightning location networks often rely on techniques like time of arrival, TOA,
TUA.
where they precisely measure the arrival times of very low-frequency VLF radio signals emitted by lightning at multiple synchronized receiving stations. By comparing these arrival times, they can triangulate the location of a lightning strike.
Triangulation, okay.
Another method is using interferometers, which measure the phase differences of very high-frequency VHF radio emissions detected by pairs of antennas to pinpoint the source of the lightning discharge. Magnetic direction finding is another common technique that uses measurements of the magnetic field produced by a lightning strike to determine its direction relative to the sensor.
Got it. Different radio frequency approaches.
Yes, exactly. Space-based lightning detection primarily utilizes optical instruments like the optical transient detector, OTD, and the lightning imaging sensor, LIS, which are designed to detect and map individual lightning flashes across the globe by observing the brief optical pulses emitted from space, as well as the geostationary lightning mapper, GLM, on the GOES-R series of satellites.
GLM, right.
Satellites like the ill-fated Tyrannus also aim to measure the electric and magnetic fields generated by lightning to study its fundamental characteristics. All these methods combined give us a much more complete picture of lightning activity worldwide.
So all these different approaches help us build a more comprehensive understanding of both the ordinary lightning we experience on the ground and these much more elusive, high-altitude TLEs. The thesis concludes by considering the challenges and exciting possibilities of detecting TLEs using small, low-cost satellites like CubeSats. What are the key takeaways for you there?
Yes. Given the increasing interest in utilizing nanosatellites for scientific research due to their significantly lower cost and easier accessibility, the thesis explores the feasibility of detecting TLEs from CubeSat platforms.
CubeSats, yeah, they're everywhere now.
They are. It discusses the inherent limitations of these small satellites in terms of their size, weight, power availability, and mission duration. It then analyzes the characteristics of the instruments that have been successfully used in previous TLE observation missions, both on larger satellites and on the ground, to recommend suitable parameters for potential CubeSat payloads.
So can they actually do it effectively?
The thesis suggests that a carefully selected combination of compact optical and radio frequency instruments with specific spectral ranges, sensitivity, and power consumption could indeed be effective for detecting and studying TLEs from these small, agile platforms. This opens up the exciting possibility of more frequent and widespread monitoring of these upper atmospheric events.
It sounds like the future of TLE research could involve a whole network of small, dedicated satellites constantly watching the skies above thunderstorms, providing us with an unprecedented view of these phenomena.
That's certainly a very real possibility. The conclusion of the thesis really underscores for you that TLEs are these incredible and often beautifully colored electrical discharges that occur high above thunderstorms, all triggered by the more familiar lightning activity below.
Right, that connection is key.
It reiterates their scientific importance in helping us understand our atmosphere's complex electrical behavior and even their potential influence on our planet's climate. And it suggests that even with the constraints of nanosatellites, we can develop innovative instruments to further explore these fascinating events.
Well, as our deep dive comes to a close, it's truly remarkable for you to reflect on the sheer power and breathtaking beauty of these high-altitude lightning phenomena. From the very real dangers that lightning poses high in our mountains to the ethereal and fleeting light shows that dance at the very edge of space, it's all part of the same electrifying story.
And the key question for you to ponder is this intricate connection between the seemingly commonplace thunderstorms we witness at ground level and these mysterious energetic events unfolding many miles above. It really makes you wonder, what other hidden wonders might our dynamic atmosphere still hold, waiting to be discovered and understood?
That's a truly inspiring thought to leave you with. The quest for knowledge is absolutely boundless, and here at the All Sorts podcast, we are deeply committed to exploring every single facet of it right alongside you, our listener.
We are indeed.
If this deep dive into the electrifying realm of high-altitude lightning has ignited your curiosity, just imagine the other incredible journeys of discovery we've already embarked on. Head over to the All Sorts podcast on YouTube right now and hit that subscribe button to become a vital part of our ever-growing community of inquisitive minds.
Please do.
Please do share this exploration with any fellow seekers of knowledge. You know, it's how we spread the wonder. And don't forget to delve into our extensive library of past deep dives. There's a universe of captivating content just waiting for you to explore.
Definitely check those out.
Stay connected with us for more behind-the-scenes glimpses and engaging discussions on X, Instagram, and Threads. Your support and engagement are what fuel our explorations, so please join us as we continue to unravel the many mysteries of our world and the cosmos beyond.